Okay, so when I open the data file for this lab, this is what it looks like. The data is not super interesting, but it's just for demonstration. So essentially what we have are a number of observations of plants. So you're a botanist today, I guess. So we have petal width in terms of if it's a flowering plant, so how wide are the petals, how long are they, and then sepal width and sepal length. I don't know what a sepal is. I suspect it's something to do with like the stem, okay? We have the species name. This is what we're going to try and predict, is what species of plant is this from its characteristics. And we have an identifier for each species as well. So I'm just going to close this. And just for reference, I'm going to have the questions open here. Okay. There are, again, a number of conceptual questions that we'll go over towards the end after we get through the script. But the data goes with problem 3. Okay. So the question is saying, build a classification tree using this data, and we're trying to predict species. And so predict the species name using the 4 physical characteristics of each specimen. Present your result or predictive model, and then interpret what it says, and then talk about things that you do. So things you need to be worried about along the way, right, as you build your predictive model. So you need to do partitioning. You think about, do I need to normalize or standardize the data or not, things like that. So you're going to obtain a decision tree, right, which is going to be a plot image in R. So you're going to need to pull that out and probably, you know, when it gets to the time of a homework, we don't have one this week, but next week we do, right? We'll do something similar with continuous predictors. So you'd want to take that image and put it into your solution file, like a Word document, right? Talk about goodness of fit measures for the model. So essentially accuracy error type measures. And then we're going to go back and using the same data, we'll try a different algorithm. So we'll try k-nearest neighbors and we'll compare their performance. Okay. So that's what I'm going to do here. So I have the script file here. Again, it's on campus, but I'm just going to open it locally. Make this bigger so everybody can see.
One question for the library, correct? Is it like based on the packages lattice and ggplot2?
It depends on those. So there are functions inside of Caret that if you call them, they need not only the functions in Caret, but also those other packages. So they're dependencies.
Because I ran the library Caret and it didn't give me any error. It just said loading package lattice and loading package ggplot. So
Yeah, that's fine. It just means it's loading the dependencies automatically, the other packages it needs. Yeah. So I've got 4 packages that I'm going to be using here. The first one, rpart, that's short for recursive partitioning, right? So yeah, recursive partitioning. So this is the decision tree package, right? Because remember, that's the name of the algorithm, the recursive partitioning algorithm. It's partitioning the data into subsets. We then have rpart.plot. This is the plotting function for decision trees to draw the picture of the tree afterwards. We then have a library called class, which is a package that has a number of different classifier algorithms in it, one of which is k-nearest neighbors. And then we have Caret, and Caret is a really big package that has a whole lot of predictive modeling algorithms, not just classifiers, but numeric predictors. It implements things like cross-validation, kind of lots of more meta stuff about your data mining process. And the reason I'm using it is one of the things it embeds is it automatically tunes hyperparameters so it can do things like I'll pick what algorithm you should use and with what parameters to get optimal predictive performance. And it'll automate that process for you. It's not necessarily so straightforward with how you use it, but I'll show you an example with k-nearest neighbors to have it automate the selection of k. Okay? I'll do that towards the end. So the first thing that I'm doing is I'm loading this data set into R. That's what this first command is, right? And I'm just using the file choose option to find the file. So I'm going to run this command on line 27. And I'm going to go to the downloaded file. Okay, and I open this, and it imports, and here it is. We have 150 observations of 6 variables. Let me If you can close it if there's an easy way. In my experience, this thing will just keep falling. Oh, that's easy. Thank you. So, first thing I'm going to do is just inspect this data to see what the imported values kind of look like. So the head function just shows the first few rows. You can actually pass it an argument, another argument, n equals, and tell it how many rows to show you, but by default it'll show you 5 or 6. 6, right? So there's the first 6 rows of my imported data set. Or of course I can use the view function to look at it like a spreadsheet, or I can just click on it and it'll open the view. Right, so here's all my data. I have 150 observations, okay, of plants. And I'm going to be trying to predict this outcome label, species name. So we have our data set. So this is our entire data set that's available to us that we can use to train and evaluate the model's performance. Remember, we don't want to use all of the data for training, right? We need to keep something aside to evaluate how well it does on data it's never seen. So the first thing we're going to do is partition this data set randomly into a training and a test set. So that's what I'm doing on the next 3 lines, right? So lines 34 through 36. I'm essentially splitting this data into 2, and I'm using a 50-50 proportional split, which is totally arbitrary. I could do 40-60 or 20-80 or whatever, right? It's up to you. But I'll be splitting this 50-50. And just to be clear about what I'm doing, so the first thing that I'm doing here, I'm essentially saying build a vector. Okay, so this command sample, essentially what it does is it randomly samples rows from a data set or a data frame. It's sampling their indices. So if I say sample from this vector a certain proportion of observations, it'll come back with a vector of that length, which contains the indices of the rows it identified in the data set I asked it to sample from. And then I can use that vector afterwards to index my data set and pull out those rows, okay, to use them in my training data. So it's going to build a vector in this case. It's sampling from 1 to the number of rows in my data. So if you imagine those are the indices for every observation. Sample 50%, or the number of rows times 0.5. And the floor function, all that's doing is if the result is a fraction, because there's an odd number of observations, it'll round down, okay, because it has to be an integer. You can't sample half of an observation. Okay, so take 50% of the values. If it happens to be a fraction, that number, round down to the next integer, and then take that many values at random from the original data, right? So it's going to make this, remember, n row. So my data had 150 observations. So this will be from 1 to 150. I'm sampling 75, and rounding down will still be 75. So it's going to sample 75 values from 1 to 150. Okay, so now I have this vector of 75 values, and it's all integers, and these are the indices of the observations that I'm going to now use for my test data. So I'm saying build a new data frame from the existing data I just imported, which is equal to the original data set, so lab4 underscore full. Remember, square brackets are indices. First value is rows, second value is columns. So I'm saying take out rows, these rows. It's a comma delimited list of numbers, which are row whatever, 5, row 15, row 21. And if I leave the columns argument blank, that means take all columns. Okay, and I'm going to now have this as my training data. There it is, 75 observations of all 6 variables. And then what I'm going to say is the rest is going to be used in tests. Remember, the minus sign in indexing says things that are not in this list. Okay, and I end up with my test data. Yes? Yeah, so this sample function pulls the values at random. Yep. So every time, so you, by the way, when you run this, you may get a different random sample than I get. Your tree may end up looking different than mine because of that. In fact, it will, most likely.
What
Yes?
would it look like if I want to add a validation set? So like,
You would make 3 partitions instead of 2. So
but like just
I wouldn't.
now you can just subtract it from the indices.
I mean, I could say build a sample from, like I could sample this, for instance, 33%, 66%. right, or 67%. Pull out the smaller one, call that train. Okay? Then I could take the other portion that's randomly determined, and now I could again randomly sample it in 2.
And then subtract and
Yeah.
do the same.
And then just as long as I keep all the observations in one of these partitions, I could use the same approach. Okay? But for here, all I'm doing is training and testing. I'm not doing this third validation step. So we have our 2 partitions now, Lab 4 training and Lab 4 testing here. You can see them in the environment window. So now that I have my partition, I can go ahead and build a tree on the training data. So that's what I'm doing on line 40. Okay. So again, the function that I call to build a decision tree is called rpart, short for recursive partitioning. I need to tell it at least 2 things. Well, actually, so it won't run unless I give it at least these first 2 arguments. The other ones have default values that will be populated if I don't specify. But I need to tell it, number 1, what data to use to build the tree, obviously, right? So I tell it use the training data. Data equals lab 4 train. The first argument here is actually the formula. So this is saying model this outcome, species name, as a function of, that's what the tilde is, and you may need to find where the tilde is on your keyboard. In European keyboards, I remember it wasn't obvious. Okay? But for me, on a US keyboard, it's the top left, shift top left, and that's a tilde, okay? So this variable, as a function of, I just list the x's or the predictors I want to use. And they're separated by plus signs, just like if I was writing a regression equation, right? Y equals this variable plus this variable plus this variable. So in this case, I'm saying predict species name as a function of petal width, petal length, sepal width, sepal length. The third argument is telling R that use the classifier method. So this means my outcome is a nominal value. It's discrete. It's a label. Okay? The alternative would be method equals ANOVA, analysis of variance. The outcome is continuous. Try and predict, because the way it does it is slightly different. Okay? As we'll talk about in the next lecture for numeric predictors, it does something slightly different. Okay, so
For class, what does it mean?
class means classifier. Yeah. So it's a classification tree as opposed to a regression tree. And then control is kind of a big parameter. It's an optional argument as well, but essentially what I'm saying is the control argument is going to take on the following values, and I need to essentially call another function that comes with the rpart package for creating the list of parameters in a way that the function knows how to read it. So that's what rpart.control is for. You specify a number of arguments here that dictate stopping rules and things, okay? And then the output of that becomes the argument that gets passed to the tree function, to the rpart function. So in this case, the only thing I'm telling it is stop splitting if you don't have at least 20 observations left in the subgroup. Okay, so if it gets to like a point where the leaf node now only has 15 observations, it'll stop branching at that point. There are other values that go in here that are default. So if you want to know what all the default values are for the stopping rules and things, the hyperparameters, you can look at the help file for the rpart function. Okay, this is just to show you an example of one. So I'm going to call this now, and I'm going to store the resulting predictive model in this variable, tree1. I haven't loaded my packages. Make sure you run the library commands. Okay, so my library is in memory, so now I'm going to go back to line 40 and run this command. Okay, it's pretty fast. Here's my tree. It's in memory, tree1. And if I look at it again, it's got a bunch of information, but 5 observations of 9 variables. It's not entirely intuitive. These are characteristics of the tree that get used for plotting. Okay. So what I'm going to do next, because this is hard to interpret, I don't interpret the raw object it spits back. Instead, I'm going to plot it. So what I'm calling now is the rpart.plot function. I'm telling it plot this tree that I just created. Type are basically formatting parameters, so you can play with that to see what the trees look like, how they change if you change the type value. Extra means provide some extra information over and above the basic tree. So that's things like how much data falls into a given leaf node, stuff like that. Or what was the proportion. And then under is another formatting thing, like where should certain pieces of information be displayed under the node, okay? So I'm going to call this, and it's going to show up in my plot window. If you get an error, something about margins, that means your plot window is not big enough. So you need to make it larger and try again. And just so I can show you, so it's very clear, let me make this small. See, error and plot new, figure margins aren't there, okay? So I need this window to be big enough. I'm calling line 45 again. There's my tree. Okay, so I can zoom in on this. And again, your tree may be different than mine because you're going to use a different random sample than me. Our data set, in the sense, in practical terms, is relatively small. So it's essentially, if you rerun the process over and over again and the tree is constantly changing, that means you need to go get more data because it's not really converging, right? Yeah, question?
Can you just go back to like line 45? Because like when you, so you plug in line 45,
Yeah.
and then you can see the tree?
Yes.
Okay, great.
If you got an error message, it may be that the window's not big enough, right?
Because you haven't loaded the libraries. It's impossible to find function or dot.
Yeah, if it's not finding the function, it means the library wasn't loaded into memory. So if you run the library command and it gives you an error, it means it's not installed. Yeah, okay. Okay. I can add it, so I can update my plot with more formatting options. So all I'm doing on line 46 is I'm saying add this as a title to the existing plot. So classification tree where min split was set to 20. Okay, and it adds this to the bottom.
Is it okay if we don't have Sedosa up in the top?
Yeah, so as I said, you may get a totally different tree than me. Yeah, right, because your sample may be different than mine, or it will be. So again, what I'm saying, if that happens, you rerun this process and you're continually getting a different tree, despite using the exact same process, that implies you don't have enough training data to capture the real relationships very well. Right? So essentially there's more noise than there is signal in your data.
Could you explain, like, just to go over, like, how you would interpret that?
Yeah, so the label here, this is the prediction, okay? So it's essentially, I think the color is darker the more confident the prediction. And this is essentially saying if you stopped at this point and didn't do any more splitting, this would be the prediction that you would get, and this is how confident it would be. That's how dark the color is, right? So it's lighter up there than down here because it's more confident down here than it is up there in its Setosa prediction.
So can you replace the whole thing you just said?
Okay, so remember, higher up the tree, the more informative the predictor that it's choosing to split on. So because it's splitting on petal width first, that means petal width was the most informative predictor in this case. And it chose to split at the point on petal width. Are you, is the petal width above, or sorry, is the petal width below 0.75 or not? If the petal width is below 0.75, you're in this group of the data. If it's above or equal to, you're in this group of the data. So this is two partitions of the training data. In this side of the training data, it decides to stop. Notice it has more than 26 observations, but it still quit, which means its test statistics said it wasn't worth splitting anymore. I'm not getting enough information gained, so I quit. Okay, so the prediction in this subgroup, if I have a test observation that has a petal width below 0.75 and I run it through this tree, it's going to give me a Setosa prediction. Right? How confident was it about this prediction? Well, 26 out of 26 cases in this group were Setosa. So it's 100% confident. Let's say I'm in the training data and my petal width is greater than or equal to 0.75. So this is a no. This thing is not true. I go this way. Now it's saying I get value from also splitting on petal width again in this subgroup. If I don't go forward, this would be the prediction I would get, right? So 25 out of 49 cases are Virginica, right? Which is somewhat of a majority, but not great. Just a bare majority, actually, just over half. But if I split again on petal width and I say, remember, left is yes, no is right. So yes, I am greater than or equal to 1.8. The prediction is now Virginica because this was true in 23 out of 24 cases in the training data that had these, well, essentially this characteristic. So it's above 0.75 and also above 1.8. So basically this means if my petal width is above 1.8, my prediction is Virginica because it's almost always true. The remaining training data has this characteristic. So essentially I am greater than or equal to 0.75 and I am less than 1.8. So I'm in that range. My prediction is versicolor because this was true in 23 out of 25 cases in the training data. Okay? No problem. Okay. So now,
So would you say those like remaining observations, let's say like the two that are missing for like the 25 for versicolor, those are probably outliers or?
not necessarily. I wouldn't call them outliers. They're just saying in this subgroup, 2 out of the 25 cases were not versicolor.
Okay.
They were something else. Okay. So now what I'm going to do, I'm changing the min split. So I'm saying keep going until you have at least, you stop having at least 10 observations in the leaf node. So this can change the resulting tree because my stopping rules are different. So we're going to call this now again, and I'll plot that tree. So we see we get some more splitting here, and now it starts to split on petal length in that second subgroup, the last one I was talking about. So instead of quitting at versicolor, it now decides, okay, if I split on petal length, I can actually do a pretty good job of figuring out those cases that I got wrong. Okay? So one of the ones it was getting right previously gets sorted into this group, and the prediction is no longer correct. But the remainder are over there, and I have 100% confidence. Okay? So it's the same tree, but it's added a split now in that bottom right subgroup, an additional split with a new variable. Is that clear? Does anybody have a question? Yeah, so notice the tree is identical. The only thing that's changed is it's now splitting here, whereas before it was stopping. It's splitting on petal length greater than or equal to 5.1. So it's decided if I take away my minimum stopping rule of 20 and change it to 10, so it's willing to go further, essentially what ends up happening is it decides there's enough information gain at this point from splitting additionally on petal length that I get improved performance that's valuable.
Like
Right.
that was in all the design commitments, but to have a different data set. I didn't even get another split.
Yeah, me neither.
Yeah, again, this is a function of my sampling data. Your tree can look different than mine. Right? I'm just saying what happened here.
So even with 3.2, we're not guaranteed to get like another split.
You're not guaranteed to, no. It depends on the information gain criteria. So in your training data, if it did split that way or any other way, would it get enough gain to be worth it? In your case, if it didn't split additionally, that means it wouldn't have. Okay. Yeah, again, it depends on your training data sample, right? The algorithm will detect different results or different test statistics with different data. And again, I'm just adding a plot with the title now. I'm adding the title rather. And what I'm doing in the third case is I'm changing the stopping parameter again and making it even lower. I'm saying keep going until there's only, you have at least 2. Okay, which means it'll get deeper now. So that's what the third tree is. And there's this updated tree. Now I'm letting it go much more complicated, right? I'm letting it get more nuanced with its splits. I have terminal nodes now that have very few observations. So basically it gets to the point where it has less than 2 and it stops. Of course, it would have to stop anyway in these cases where there's only 1 observation left because there's no way to split 1. But these other ones, for example, it could have in theory proceeded on this and it won't because my stopping rule made it quit. So it gets more complicated. Basically, it's figuring out isolated cases in these groups that already had a pretty big majority to begin with. So I would say your tree's probably getting, if we start to do validation on this thing and pruning and stuff like that, you might find that general performance of the tree is better if we throw away some of these like very nuanced minor branches, right? That would be likely. But just see if I change my stopping rules, the algorithm will arrive at a different solution. And again, this is the tree with a minimum split of 2. Okay, any questions so far? Other questions? No? Okay. So again, this is, the tree's only being trained on 75 observations. At random, we haven't evaluated the performance yet. This is just what it comes up with from the training data.
In a certain way, like the less branches you
It doesn't, I don't think, you can't say anything about how good the tree is from the number of branches it's making. All of that's going to come from when you evaluate its performance on holdout data.
Okay.
So before we get there, I just want to do one tree here, which I'm calling a garbage tree. I'm doing the same thing, but if you want to do a predictive model based on every available predictor, you can put a dot here, and that means use everything. So I'm going to train a tree to predict species name as a function of every available predictor using this lab data. It's a classifier again. I'm not giving it any stopping rules, so it'll have some default values it'll use, and I'm going to build that tree. Okay, and I'm going to plot it. Here's what it looks like. Notice in the plotting stage, I changed some of the arguments here, so I didn't tell it what type of tree to make or the formatting, so it looks slightly different now, right? Because these are default formatting rules. It's saying, so why is this a garbage tree? What's wrong with this?
It's using the ID, no?
Yeah, right. So remember, I had a column in there which was species ID, which is just a numeric indicator of the species. It's getting 100% prediction because the ID is 100% accurate to predict the label, because they're basically the same thing. So be careful about what variables you put into your predictive model. Generally speaking, I do not suggest ever saying use everything, because if you're not paying attention, you may get what looks like an awesome model, which, by the way, will also do really, really well on the test data. So you think it's great, I can do perfect prediction, let's go. And then you're not paying attention to the fact that this variable, this ID information, is not available in the wild. Okay? So be careful. Okay. So now I actually need to evaluate how is my tree doing. So I'm going back to the first tree when I do this, just because. And what I'm going to do is I'm going to generate predictions from that tree using the test data. So I built the tree with the training data. I have these other 75 observations that are held out from the beginning that I didn't do anything with. Lab 4 test. So now I'm going to use that test data and the tree I built and generate predictions on the test data, okay, for the species label. So what I'm doing here is I'm saying add a new column to lab 4 tests, right, using the $ index. I'm indexing a column that doesn't exist yet, which basically it figures out I mean add a new column. I'm calling it PRED, short for predictions, and populate it with this. There's a function called predict. Okay. Generate predictions, right? That's what it's for. Where are the predictions coming from? Use this tree that I trained earlier. Generate the predictions using this data. Okay. And it's going to look in this data, and it's going to basically the splits that the tree contains. It's going to use that tree's splits, find the same values in the test data, so the same columns and split values, and apply the algorithm basically that it came up with, the branching process. And then depending on the leaf node that a given test observation falls into in that tree, spit out the prediction. Okay, and it's a class prediction again, because I used a classifier to train this thing. So it knows to spit out a discrete value. Okay, so because I'm telling it to use class, that means it's going to spit out, you know, the same idea of like the majority outcome, the voting rule is the determinant of the prediction. Okay, so I'm going to do this, and it's going to populate predictions for each test observation in a new column called PRED from that tree. So if I go here, we see we now have 7 variables instead of 6 in the lab 4 test. So if I open it up, here's the predictions, here's the actuals. Okay, and now I'm going to compare these to see how well or bad did it do in the test data. So if these things disagree, that's an error, obviously, right? And if they're the same, it's a correct prediction. Now, I have 3 outcomes here instead of 2. Is it possible for me to make a confusion matrix now?
What?
Can I make a confusion matrix if I have 3 labels?
No, it's only 4.
Oh no, so the example I was using before only had 2 labels.
Oh, so yes, 3 by 3.
Exactly, so it's the same idea, except I'm going to have 3 by 3. So for each prediction, what type of error did I make? it gets more complicated, so you can't talk in the same way about precision of a particular label. I mean, you can, it's just, it's no longer correct versus incorrect. It's now correct versus multiple types of being incorrect, right? You'll see what I mean. I'm going to make the confusion matrix here. I'm calling this table command to create the cross tabulation of predictions and actuals. So you can actually see the cases where they are agreeing, where they're disagreeing, and how. Remember, this table command was one of the commands that we had in the first lab, right? So it just shows the count of observations that contain this unique value. Okay, and when I pass two variables, it's a cross tabulation, so combination of two unique values across two columns. So we'll just call this, and there's our confusion matrix, okay? So it's the same idea as before, right? So we have actuals and predicted. So be careful. If you pass it the wrong columns in the wrong order, it'll put predicted here and actuals up there. So pay attention because you may get your cells mixed up, okay, depending on that. So this is saying it got every prediction in the test data for Setosa correct. It got every prediction for Virginica in the test data correct using this tree. Well, sorry, no. It got 22 of them correct. 3 of them were wrong. So so given it's actually Virginica, it predicted it correctly 22 times, right, out of the 25, and 3 of them were wrong. It predicted them to be versicolor when they were not. And then lastly, it got all the versicolor predictions correct. Okay, is that clear? So it's doing pretty well. So accuracy would be add these up, and then this plus 3 is the denominator. That's the proportion of correct predictions. 3 out of the total number of 75 observations is the error rate, right? You could figure out precision of Setosa is 100%. So given I predict Setosa, I'm correct 100% of the time. Given I predict Virginica, I'm correct 100% of the time. And given I predict versicolor, I'm making errors now. So my precision stops being 100%. Yes?
Is there a way, because that looks like a very good model, is there a way, well, yeah, I haven't gotten to this great analysis, but that looks like it predicted 100% Setosa and 100% versicolor. But that also depends on your random sample, because for example, mine is not as great of a predictor. Like, can you create a code to like run it 4 times, for example, to see like have 4 different random samples, or how many, like how do we know how many random samples we need to see whether it's good or not? You know, it's a bit of a.
So you can, so there's a few things you can do. So number one is if you repeat the whole process and your tree keeps changing, that means you don't have enough data. Because it shouldn't be that unstable. You should be arriving at a pretty homogeneous predictive model with the process if there's enough data for it to figure out the relationships. So that's one thing. If you rerun this tree so if you take this tree, generally speaking, what you're talking about is something we would address with a process called, well, you could add a third partition like we talked about earlier called like a validation step, where you select your tree, you see if it's doing well. Okay, now I'm going to show it the third partition that it hasn't seen before and see how it does. And if it's really bad there, that suggests that actually it's not that stable. This is not informative. Okay. There's also this idea that we don't talk about in this class called cross-validation, which essentially repeats the whole process in a nesting structure where instead of, say, taking training, test, validation, you do that, but then you repeat the whole process with 3 new random partitions, and then again with 3 new random partitions. And you essentially see how stable are the results across each of those. And the more unstable it is, basically you know you're not really in good territory. Okay? So yeah, you wouldn't just do this as a one-off and stop. Although that's how we're doing it here, because this is how people initially did it when they first started figuring out predictive models, but then you realize it can be unstable. Okay? So this is the confusion matrix that my first decision tree is giving back in my test data. Again, your results may look different because your tree is different or your test data is different. So now what we need to do, so before I go forward, quick thought. I didn't scale my data. Did I need to do that?
For this, no. Like for this approach that we used.
Yeah, so there's no distance calculations here. So scaling doesn't make any difference. If you did scale, it wouldn't do anything bad, right? But it doesn't help you in any way. It's not important with decision trees. I'm going to run k nearest neighbors now. It will be important there, right? Because neighbors are all determined by distance. Okay? So, to make my models truly comparable with one another, I'm going to use the exact same partition. The reason being is that it's kind of unfair if my k nearest neighbors implementation is using different data than the decision trees data algorithm was. I'm now not just comparing how well does one algorithm do versus the other, I'm also comparing how does this one with the data it got do against this one with the data it got, which are not agreeing. It's hard for me to disentangle, is it the algorithm that's better or did it have better data to work with? So typically when you compare algorithms, it's generally going to be done using the same data. Okay? But the first thing I need to do, so all I'm doing, I'm reading in the data set again. You don't really need to do that. I just have this line here in case this is where you wanted to come back to the lab and start from. I've already got the lab 4 full here, right? It's still there. I didn't change any of these values before. It's just the original data set. So I'm skipping the line for now, but you can read your data in again if you'd like to. First thing I'm doing, I'm coming up with maximum values observed for each column. There's no theoretical maximum for petal width. Maybe there is, but I'm not a botanist and I don't know what it is. So all I'm using for my scaling basis is what's the observed maximum value. Scale with respect to that. Okay. So I'm getting the maximal values for each of the 4 variables that I'm using as my predictors. So you can see what they look like here. Okay. So the first one, and again, so this is petal width, the maximum value is 2.5. Petal length, the maximum value is 6.9. Sepal length 4.4, sepal width 4.4, sepal length 7.9. And now I'm scaling with respect to those values. I mean, the more efficient thing to do would have been for me to store these values into a list and then pass that list down here as the upper bounds for the scaling process. And remember, the scaling, what it's going to do by default is standardize the data. So essentially, take with respect to this maximum and the minimum observed value in the column, what proportion am I in that range with the value that this thing had? So I'm scaling everything down to being between 0 and 1. Okay, and again, I'm not going to mean center the values because I don't need that for this process. And I'm applying this to the numeric columns 2 through 5, right? So these 4 things that I was talking about a second ago, my 4 predictors. I'm storing the results in the same columns of the original data set. So I'm overwriting the values with their scaled versions. Okay, so if I go back and look at this data set, so now it's all proportions between 0 and 1.
Sorry.
Yes.
Question, like in that line, why do you already specify which columns to look at when defining the variable on the left side? We go back.
Well, I'm telling it, take the scaled versions and put them, overwrite their values in the original data. Remember, these are columns 2 through 5 in my data set, so I'm saying whatever those columns are right now, right on top of them, replace them with the scaled values.
With the scale.
Yeah.
Okay. In order to have like the...
You could also just make these as new columns in the data set and use those instead. It doesn't really matter. I chose to overwrite the values here. Okay. Now again, to be fair, I'm using the same random sample, so the same vector I made originally for my partitioning process. And now the reason I'm recreating the training and test data using that index is because the values are scaled this time. Right? So otherwise I could just reuse them as before. Okay, so now my training and test data, again, it's still the same 50-50 split, the same rows, but the rows are now scaled values for my x's. Now, note, I'm not scaling the outcome. Obviously, it wouldn't be very easy to figure out how to do that anyway, because it's a string, right? It's a text label. Even if it was a 1 and a 0, scaling wouldn't change anything, actually, so it's not a big deal regardless. This is just a side note I'm not worried about here, just showing how you could pull out specific columns if you wanted to with indexing. That's not a big deal. You could ignore that comment. And I'm coming down here, Line 98 is where I'm trying out the k-nearest neighbors algorithm. And remember, there's nothing to train with k-nearest neighbors. All there is a value of k. So I'm saying, I'm passing it a value of k that I've arbitrarily chosen, and I could try different values of k and look at the confusion matrix to see what's the best one, right, in terms of performance. All I'm going to do is say, run k-nearest neighbors. Here's the training data for each test observation, right? I'm trying to come up with values of predicted values for species. So it's lazy, right? So I'm going right to the prediction step. There's nothing for me to do before that. It's just two data sets and a value of k. So I'm saying spit out predictions using k equal this and these two data sets. And I'm going to create the confusion matrix and see how it looks. This is a much simpler process. Note that, again, we don't want this thing to create distance calculations including species ID, because that's not really meaningful. So that's why I'm telling it don't use the first column, right? Because that was the species ID column. So you need to be careful. This is equivalent to saying when I called decision tree and put a dot in and said use everything for predictors. If you don't pay attention, you're going to accidentally use it, and you're going to get different answers, but they're not right answers. Okay, so what I'm saying is call k-nearest neighbors using this training data, generate predictions for values or observations in the test data. And it's asking what's the class label. That's what CL is short for, class label, the thing it's trying to predict, and what k value to use. Okay, so it's going to look at 8 nearest neighbors. This is arbitrary.
Yeah, it's just what you just.
I'm just putting in a value. Yeah. Okay, and it'll store the predictions in KNN underscore PRED.
We're probably gonna go into it afterwards, but why don't we do it as we did it with the cluster analysis, where you do iterative?
You could.
You could
The problem is,
just to fill like a matrix to see which one would fit the best.
Yeah, you could create various columns with all the performance metrics you might care about, like precision on a given class, recall on a given class, overall accuracy and error, the F-score thing I talked about that combines precision and recall. You could store all of these and just iterate over every possible value of k and then see which one does best, but you're going to get into a situation where it's not clear. Like, depending on the metric you care about, you'll come to a different answer. So generally speaking, it's not like you're going to get a uniform solution that's the best one, which is actually technically true with clustering too. Depending on the metric you look at, you may come to a different solution or conclusion about the right value of
So
k.
the weighting that I might, like, put in
Exactly.
parameters.
So you need to come to this with what are the error measures I really care about with my model in the setting I'm going to use it. And then you might use that approach to choose k, for example, that optimizes that measure. Yeah. So you could do that. The same kind of for loop we did last time could be used here. I'm converting it into a matrix because if I don't, well, the formatting may not be particularly to my liking, so just to see what it looks like. Okay. I think this is fine actually, but the thing is I want to convert it into a matrix because it'll then be able to process it in the table command to make my confusion matrix. Okay, so I'm going to run line 98 and store these predictions. You just see them here, but I'm going to store them in a vector for KNN underscore PRED. Okay, here it is, 1 to 75, so my 75 predictions using k nearest neighbors. And then I'm going to pass this to the table command, and I'm going to have cross-tabulation of the actual species name with the prediction for the test observations. This DNN command is, again, all this is doing is giving it titles. Okay, so these are the actuals, these are the predicted. Performs pretty similarly, does marginally better in this case for me. One of these predictions is now not wrong, whereas before it was wrong with the decision tree. This is a pretty marginal difference. Like, I'd have a hard time saying that this one's way better than that one. I can try changing my value of k. Let's see what happens when I do that. So let's try a k of 2. I'm going to rerun this and then get a confusion matrix. Does just as well. Let's see if I can make it break. K of 40. Well,
So
the
you
data is
really
just very
play
easy.
around with the parameters.
I'm just trying to make it mess up, but this thing does pretty well with any of the data because this basically means if you were to cluster this data, they're going to be very far apart from each other.
Okay.
If you clustered it in terms of these 4 dimensions, they're highly separated, which means it's very easy to predict the label from the characteristics because they're so separate from each other, right? There we go. Now it starts to mess up. So I told it to use k of 60 out of the 75 observations, right? I'm getting towards naive majority now. It's making a ton of errors all of a sudden. Okay. So this is just illustrating the idea about how you would evaluate k. Okay. Any questions about this?
When I do 50 and when I do 60, the actuals, it always predicts the first term.
For everything. Okay. That just means your training data was not representative. Yeah. Okay. So we talked about a way you might manually iterate over k and try different values. As I said, Caret is a package that's good to know about because it implements many different predictive modeling algorithms and also the means to automate selection of the optimal combination of parameters. So k-nearest neighbors doesn't really have a lot of parameters. You can play with things like what's the prediction threshold. You can also play with k. Decision trees has a lot more things that you can play with for stopping rules and stuff. The point is you could use a package like Caret to automate the selection of optimal values for all the different parameters. But it's a brute force thing. So essentially what it does, imagine you have 2 parameters you care about choosing. It'll try every possible combination of those 2 parameters and then look at the performance metrics and choose the 2 that do the best together. If you have 5 or 10 parameters to choose from, it looks at every possible combination of 5 or 10 parameters. You can imagine this explodes quickly in terms of how much computational processing is needed to try all those different parameters, especially with a big data set. Okay? It can get really slow and bogged down. It can take a really long time, the more parameters you pass it to look at. And be careful as well because there may be multiple outcome metrics that you might evaluate its performance based on, right? So you need it to like recover and maybe store all of those for each combination. So it gets pretty complicated. But I'll show you how you can do that anyway, just to be aware of sort of how it works. So I'm doing KNN again, but this time I'm using the Caret package to do it. And the function that you use is called train. Okay? And because KNN is simple, all it's going to do by default is find the optimal k for me automatically. It'll try every possible value of k and come back with what it thinks is the best one. Now, how is it doing that? Well, you want to read the help package to see what's the default criteria it uses to select an optimal k. Okay? Don't just trust it to be right, because it may be optimizing something that you don't care about. You may want it to care about a specific type of error, for example. So I'm going to use this. I'm saying call the train function from Caret. Here's the predictive model. So predict species name using these 4 inputs, so it looks like my decision tree function before, right? Use this training data, and your method is going to be KNN. Now notice I'm not giving it any testing data yet. So what it's actually doing in this process is trying different random partitions in the training data. So it's doing its own partitioning process here. And then when it's done selecting k, I can take it and try it on my holdout test data. So it's almost like I'm nesting something now. So it's trying lots of different partitions to select k that does the best. In this training data, it's partitioning the 75 into 2 or 60-40 or whatever it is. It picks k based on that, and then now I've got another 75 observations that it doesn't know about that I'm going to see how does this thing do. So it's already nesting now, right, unlike before. And I'm telling it what method to use. This is where I tell it what algorithm to use. In this case, I'm saying use k-nearest neighbors. There's other ones I could pass it, right? So for instance, there's one called Ranger, which is for an advanced version of decision trees. Okay, so I'm going to call this, store the output in KNN_train. So it's still pretty fast. It takes like a second this time instead of a fraction of a second. The data is not big. Okay, KNN train is here. So this is the outcome. It is not a set of predictions. It's not a data set. It's an object that has meta characteristics, right? It's the solution it came up with. So it's saying the method used was k-nearest neighbors. Here's the parameters. In this case, it's one parameter, a factor with one level, so it's k. It's trying to optimize k, right? Yes.
Not working with the KNN train from this, or should I put KNN flag or no?
No. What's the error you're getting?
Error in train, impossible to find the function train.
That means that Caret is not loaded into memory, the Caret package. Now again, this is an object and I can reference meta characteristics of the solution it came up with. That's what I'm doing next. So if I type in knn underscore train, right, this is the object I got back a second ago, and I put a $, it pops up with a help thing. It shows me the characteristics I can ask for, right, from this object. So I can get predictions, the metric it's using, the final model, training data it used, resampling process, all kinds of random stuff. But what I want is best tune. So this is the parameters that it came up with that were the best choice of parameters. Oh, what's it trying to do? Trying to draw something.
It still gives you the result for K as well.
Yeah, but I don't know why it's giving me this warning. Oh, because it's trying, every time I run a command, it tries to redraw my plot that's in the plot window. So that's why it's complaining about the tree not having enough space. So I'm just clearing that. Yeah, so my best K it actually decided was 9 based on this sort of nested cross-validation process. Okay. So I can now just go back to the original data and I'm going to give it the holdout data. And I'm going to use a K of 9 and see how does it do in my holdout data. Okay, to get a confusion matrix and things back. So predict using this object I got back. So the best solution model that came back from the train function. And predict can accept a number of kinds of inputs. When I give it an input that's like a caret object, then what it wants to know is what's the output going to be? It's going to be the lab4 test, right? So this is basically the data to evaluate it on, to generate predictions in. The parameter is called new data. And I'm storing again the output in this knn underscore predict vector. Okay, so now the outcomes are factors. They're levels, right? So they're nominal prediction outcomes. I can see them over here, knn predict. And if I want to, I can now create cross tabulations. So my confusion matrix again. So I'm creating the cross tabulation of actual species name with predicted as before. And it basically does just as well. Okay, I'm not getting a lot of improvement here. You don't really start to see big benefits unless you have sort of a bigger, complicated data set. Right? But this is just sort of for illustration purposes. Okay. Any questions about that process? So you don't need to know how to use caret for this class. That's for your benefit, right? That it can actually make your life easier if you try and use this stuff in practice. That it automates hyperparameter tuning, selecting the best combination of hyperparameters. Okay. And it's a complicated package, so I encourage you to take a look at the help file if you're not entirely sure how to use it. Last thing I'm going to do is build a lift chart. So what I'm going to do for this purpose, lift charts generally make the most sense, or they're the easiest to follow when it's a binary outcome. I'm trying to find a certain label that I care about. So what I'm going to do, I'm going to pretend that what I really care about is Virginica. Is it a Virginica or not? How easily can I detect Virginica? That's what I'm going to be doing with my lift chart. Okay? So what I'm going to do is I'm going to take the original data set. I'm just putting it into a new data set that I'm calling a binary because it's the binary outcome version of it. And I'm going to create a new column called Virginica, which is 1 if this is a Virginica and 0 if it's not, if it's either of the other two species. Right, so this is an if-else statement. So if in this column the value equals 2 for the ID, then we're going to populate a 1 in this new variable. Otherwise, if it's either of the other values, we'll make it a 0. Okay, I'm using the same data as before, the same partition. Okay. Now what I'm going to do, I'm going to create a new tree that all it tries to do is predict, is this a Virginica or not?
So just really quickly, you said before like 2, 1, and 0. Why don't I only have 1 and 0? What is it? 2, 1.
This is an if-else statement. So if the value of species ID is 2, then populate the new variable with a 1. Otherwise, populate it with a 0.
Okay.
Yes or no, this is Virginica.
Okay.
Okay. So regression tree predicting Virginica from the 4 characteristics using the training data. And plot it. There it is. Okay. So based on sepal width, petal width, those are the 2 things it decides it needs to split on to reliably predict. 0 is it's not Virginica, 1 is it is Virginica, and these are actually just showing me proportions. What formatting did I use here? I need to tell it, sorry, class equals, or method equals class. Because otherwise, by default, it's doing a continuous prediction. So remember this method equals class argument that I was using earlier? Where are we? Method equals class. And I need to remember to say that so it knows it's a discrete outcome. Right, so I'm adding method equals class. Let's do this again. Build the tree, plot it. Okay, like before, right? The prediction is a 0 or a 1, depending on the leaf node I fell into. And then this is essentially saying this is 59% of the training data, 13% of the training data, 28% of the training data. This had 90% confidence that it would be a 1, so 9 out of 10 cases are 1s. This is all 0s. And this is 1 in 9 cases are 0s. Or sorry, 1 in 9 cases are 1s. They're mostly 0s.
So this tells me that 28% of my data set are very likely, or like with a 0.9 over 1 probability that it's Virginica.
Yeah, and it's the data specifically that had those characteristics, those splits. Okay. Generate my predictions like before. In this case, I'm saying don't give me class predictions. So don't give me 1s and 0s. Actually, give me the probabilities, the confidences that you got. Right? So how confident were you in a given prediction? Now I can rank order on that confidence, right? In the data, in the test data for my lift chart. So I have a continuous set of probabilities now. So the probability, the majority outcome. So it'll all be, in this case, every prediction is going to have a confidence of 90%, 100%, or 11%. Right? Those are the three only possibilities here. Reorder my data based on this value in descending order. Remember, the lift chart is if I rank order based on this versus if I just use a random ordering. I'm going to compare those two. Store the outcome, so overwrite the data where it's now been rank ordered based on the probability or the confidence of being a 1 based on my model. Subscript out of bounds. What happened? One second. Because there's two classes. So I need to tell it which one. So rank order based on being a 1 is what I want. Okay, so I have to index it, right? So when I ask the predictive model to give me back those confidence probabilities, it gives me two of them, the one for a 0 and the one for a 1, right? So I need to tell it which one do I care about. So that's what I'm doing is I'm passing an index. Because this is actually not it's not a vector, it's a more complicated data structure. It's two vectors that are together. So I'm telling it which vector to use. So 1 as opposed to 2. So the indices, the first one is the probability that it's a 0. The second one's the probability that it's a 1. So what I've done is if I give it this 1, it's going to rank order biggest to smallest based on the probability that it's a 0. If I pass it a 2, it's going to rank order observations based on the probability that the value is a 1. I'll update the script on campus, by the way, because I just...
And if it's a 1, sorry.
A 1 is Virginica. So the probability that this thing's predicted probability that this thing is a Virginica.
Okay, with research.
Yep. So I'm rank ordering based on that probability now.
But like 2 as well as 0 would mean it's not Virginica, but it's not defining which one it would be.
It's just saying not Virginica.
Okay.
Yeah.
Like two different kinds of not Virginica.
I could be wrong in more than one way, or the probability might be... It's not clear which other species this thing is, but it's not this. Now I'm constructing variables that are going to go into my plot. Okay? So essentially, what I need to do is I'm calculating the random result. So what this is going to be is what proportion of the data is a Virginica in the sample. Right? That proportion is going to be equal to my probability that any given thing I draw at random has that characteristic. So if 40% of the data are Virginica, right, then there's a 40% chance that anything I'd randomly draw will be Virginica if I'm randomly drawing. right? Or if 1 out of 2, then every other one is going to be a Virginica with a random draw. That's the expectation at least. Okay? So I'm building essentially the reference line in my lift chart, the rate of detection that I would expect to get if I was randomly sorting plants. How often am I going to find Virginicas, or at what rate as I progress through the population with a random sorting? So that's what this variable's basically creating. Okay. And then I'm plotting, right? This one's actually saying, so the first one is the reference line. The second one is what's the rate that I'm actually detecting them at in my rank ordering, right? So I rank order based on my tree, and then what's the proportion of Virginicas in the sorted list as I progress down it? And I'm going to plot those two lines against each other. I'm basically manually building the lift chart. This is a visualization function you don't need to be worried about. We're going to come back and talk about ggplot at the very end of the class when we talk about visualizations. It's much more flexible and functional than the standard plot function. Okay? So don't worry about this too much. Essentially, I'm telling it to plot this data, the two variables that I care about, right? Y over x. I need to make this thing bigger. Missing geom path. What's going on? Okay, I'll fix this code because it's breaking since I changed that earlier line. So yours is plotting. Why is mine not plotting? Maybe my plot window is just too small. No, there's something weird going on with mine. Is it working for other people?
For me, it's not.
No, it's not supposed to be working. So I'll fix this portion of it and update the video later just so you guys can make sure you know how to do this. So we're out of time. So I'll also, in my recording, I'll include the discussion about the other lab questions, just so you guys have those. There's no homework based on this lab anyway, but it'll be useful for the next one, potentially, just conceptually. So we'll talk about interpreting this lift chart, and then I'll also talk about how you would calculate precision recall with this matrix, okay? That'll be in the video that I'll post online later. Any questions before we stop? I don't want to take you guys over time.